Okay, so good morning, everybody. This now works, excellent. I'll just go use my own laptop. We haven't had technical difficulties earlier. So I'm going to talk about forming FFPs in transformation models that have a lot of what you've talked about in that lovely review talk there, especially like parallel accretion and migration. These are all things that actually go into the full transformation models that then go through and actually form the planets that then get ejected. That gives you an FFP mass function. Basically. So just quickly on this bit, we all know what FFPs are. So planetary size objects or one finalist planetary size objects. They're not bound to any star or brown dwarf. How they actually form is very unknown. There's a large mass range in observations. You've got the super Jupiters, and now we're going down to terrestrial planets. Do they form through star formation processes, which is more applicable to the giant planets, or do they form through planet formation processes similar to core accretion mold, which is what you just spoke about? Is there a wide diversity in FFPs? Should we be expecting that, especially in terms of compositions as well, for all the future work? And then how well do the FFP distributions, the mass functions especially, match the bound exoplanet populations, which will be important in future works when comparing to things like Kepler, things like Plato. There's going to add a lot more planets, even to the Roman survey for transiting planets in the future as well, which I think Scott mentioned that other conferences is going to give 100,000 planets. So there's a lot there to compare in the future. What are the differences between? Okay, so just from the observations, yeah, so we've now got this. We heard a lot about this yesterday, where we've got some observations of low mass planets, and then we've got a lot of high mass planets in the observations from microlensing. Currently, there's an expected that there's this expected slope, as Eve just showed as well, that goes -1 slope going towards the lower mass. And here's just a formulation of that from Nakanoshimi's paper. So, how do we form FFPs? As I said, there's two different routes. You've got star formation, you've got the planet formation routes. More massive objects can form similar to stars, so that's just core collapse effectively. Whereas the smaller planets, they can't really go through that process. They have to form through planet formation processes. So this has to be something similar to the core accretion model, and then they have to get ejected from the parent system somehow, either through interactions with other planets, interactions with other stars, interactions with flyby stars. All these different ways are going to add to what we see in the observations. Most planet formation models at the minute, though, they use predefined distributions of planets, whether you put in sort of a solar system, you put in the bound exoplanet population, so what's from the Kepler, or even when you do the formations side of things and you go, okay, I'm going to start with Mars mass, lunar mass embryos, it kind of misses out a lot of things of actually forming these embryos as well. And so actually, they already use formed planets, effectively. So one of the things that I focus on a lot on this is trying to get rid of this assumption and actually start with no embryos in the disk. And they actually form through what's known as spinning spheres and gravitational clouds. So the other thing I try and do in a lot of this is actually focus on the possibility of formation of the FFPs rather than just the occurrence rates and properties or how they form effectively. So a lot of this work is based on, so this talk is based on two papers. So the first paper is one earlier in the year, which looks at formation of FFPs from circumbinary systems. And so in this area, I'll talk about more masses of FFPs produced, how often they're produced, where they come from in this. And like I said, these include the planet formation processes. So it should give a better representation of FFP efficiencies. And then later on, I'll talk about from work with Will, where we then use a lot of those models to then go and actually try and make a galactic population of FFPs to actually try and see if we can do a good first guess, good first stab at actually trying to then compare with the observations that we currently have in preparation for Roman in the future. And so this includes some assumptions for wide binary systems and for simple systems based on the circumbinary simulations I've performed. Okay, so just basic models, it's a big slide. Basic models, so I use the Mercury 6 N-body integrator. So this is full 3D. This includes the effects of the central binary on each other and on planets. There's a thermally evolving viscous circumbinary disk, similar to what you've shown before. This also includes a central circumbinary cavity where the gas is perturbed out of the orbit. So you essentially have a cavity about 3 to 4 times the binary separation there, where anything that goes in is in the dynamical instability limit and it gets chucked out very quickly. So it's essentially a no-go zone. There's also photoevaporation. So this is high energy radiation coming from both the central stars in this case. So this is X-rays effectively from there, and also from nearby stars. So this could be O stars, B stars. In the nearby, you've got star-forming region that act to remove the gas from the disk. And actually, this is actually what drives most of the gas removal of the disk, infrastructure disk generally, unless you're in very weak environments. And then the either viscosity or MHD winds will take over. So like I say, I start with a gas and a dust disk effectively. Then I include a pebble, the planetesimal and embryo formation model. So this is based on pebbles forming in a disk, drifting, getting collected, trapped at certain points in disk for very short times, like 1500 orbital periods. And there they have enough mass to then undergo gravitational collapse and form planetary embryos and planetesimals. Generally, these embryos are somewhere between the order of 10 to minus 5 to 10 to minus 2 Earth masses. 10 to minus 3 Earth masses. So that's Vesta to Pluto. Once they form, they can then start creating pebbles, as you showed before. As pebbles drift past, they accrete onto the planets. They can also accrete the planetesimals that are also forming in the system as well. And then as they get above an Earth mass, they're allowed to accrete a gaseous envelope, and that's when they start efficiently doing that once they get to about 10, 15 Earth masses. And then there's also planet migration involved in the models for embedded planets, which is what we've referred to as type 1 earlier, so it's type 1 migration. And then also once planets get massive enough, they open gaps in the disk, and this is referred to as type 2 migration. Generally, the type 2 is a lot slower than type 1. So just a quick thing on the setup. Stars are based on Bell 1 system because I already had to set up the circuit binary setup for this, and this is important for knowing the parameters to actually parameterize the cavity in a 1D disk model, which becomes a little bit awkward. But the fits are generally quite good to what is seen in hydrodynamic models. And then we vary some initial alpha parameter. There's the separation, the disk mass, and UV field, which is the external radiation field in the starting region. Okay, so I'll show you moving this up. So this shows just the first snapshot. You see here a few planets have already formed. When it starts playing, I'll talk through it, but if you see a gray point, that's a collision. If you see a red cross, that's a ejection from the binary, and a black cross is ejection from planet-planet scatter. Okay. So as we play the movie, we sort of see all these planets are then forming. They start accreting the pebbles, as you see here. And then once they get to about an Earth mass, they start migrating. This will come through again in a minute as well. And then as they start getting here, they start accreting and hitting each other. And then you get a couple of giant planets forming and start migrating in type 2 up here. And you kind of see there's a lot of collisions in gray. Few of the ejections here from interaction with binary. And then you've got another couple here that are effectively planet-planet scatters. Okay, so just as they do that, they run through again. That's 14 years. We'll go through again. So just go through it quickly. That's fine. You sort of see these ones still moving out, but still accreting slightly. So see here, like I say, you form accrete pebbles, migrate inwards, hit, and you interact with each other. Here they get caught at this certain binary cavity, and that's why they get this little bit of trapping. And you get a lot of dynamic interactions here that kicks some out. This one here, which went out actually from planet-planet scatter in the end, but probably with the interaction with that giant planet. And then we get this left over after 4 years. These ran for 10 million years, so I can't remember what the fate of these two objects was. One of these, I think, might have been, this one might have also been ejected onto from interaction with the stars. So this is generally the picture of what I see in a lot of simulations of ones that actually form planets. You see this kind of form, accrete, migrate, and somehow get ejected. Okay. So looking at the population as a whole, this essentially shows the pericenter distance. So this is where the planets were ejected in each simulation and their planet mass. So you kind of see here there's a large diversity in planet masses, down from 10 to minus 5, all the way up to 10 to the, I think the highest was 2,000, which might be that point one. So that's 6 Jupiter masses in this case. And you kind of see this kind of 3 distinct populations. So you've got this nice little low mass set of planets here, which are ejected through interactions with a binary. You have the high mass population of giants, which then interacts with the disk a lot more as they go out. So that changes their velocities as they're going, which kind of gives you this massive skewed area here in terms of the parameter space. And then we have this low mass stuff from further out in the disk, which is essentially from planet scatters. Okay, and generally, from comparing this to single star simulations, sorry, these are generally quite a good match to what I actually see in those simulations as well. So actually, from these simulations, these are a good proxy for what happens in single star systems. And so just going to the points yesterday, just showing that this is then the velocity dispersion. So I get from effectively the blue line showing the planet scatter is generally averaging around 3 kilometers a second. And then for the binaries, which is hidden underneath the yellow line here, which contribute the majority of the planets, that's generally around 10 to 15 kilometers a second. So this comparison with the bound planets, as we can sort of see here on this cumulative distribution functions, there's not as much comparison between the eject planets and all the bound planets. But when you compare to those close to the star, where that's close to the binary in the region where actually planets have been ejected generally, we can kind of actually see for anything about 20, 25 Earth masses, there's a very nice fit. So this is a good test of actual, when Roman gets some data and we can actually see what these distribution functions look like. Compare that to the bound transit, bound radial velocity surveys and see how good this fits, see if that can give us any information on the planet formation processes that need improving or we need to understand it. Okay, so this, like I said, would be useful comparing with Plato and the other Roman missions. Okay, so as I said, most of the planets are ejected through the binary, and this is actually also depending on your planet mass. So super Earths or anything above an Earth mass is generally ejected through interaction through the binary, and that's mainly as a factor of migration. They're migrating into towards cavity, interacting with each other, then interacting with each other. Whereas the low mass planets are generally ejected, or more, not generally, but more often ejected by planet scatter. And we sort of see this big peak around the super Earth. Okay, so that was that paper. So now just moving on to the building the galactic population. So to do this, we now need to actually know, okay, how many stars are in binary? So this is all based on certain binary simulations. So for certain type stars, 60% of stars are found to be in binary. The distribution of the separations is found to be a log normal. So generally, I follow the black line here for the FGK line from Raghavan 2010 paper for looking at the separations. And this allows me to then go, okay, this many are certain binary, this many are the Y binary, and it's intermediate between. So just going on that, to do that, we then, like I said, separated our distributions out. We have 23% of our galactic population of circle binaries, 25% of Y binaries, and what I classify as 380. And that's because effectively, once you get the outer binary out past there, it doesn't interact with the planet formation processes too much. And in terms of changing the overall planet mass that comes out at the end. And then these intermediate binaries are the ones between where it's a bit awkward to kind of guess or to judge how the planet formation processes are affected because you can have large certain binary cavities, so in terms of both rapid open dominate there, or you have extreme truncation of the circumstellar disk. So just go on here. And so then when we look at this population, we find actually circle binaries provide most of the planets. So provide not about 10 planets per system, which gives about 1.3 per star. The ultra wide binaries is still a couple per system and only 0.3, and the single stars only actually eject about 1 planet per system. This is all above, I think, 10 to minus 2, so lunar mass. So overall, we only get about 2 planets above a lunar mass per star. I think for an Earth, around 0.3 Earth masses is about 1 planet. Okay, so just going on this is the main plot. So this is just looking at this mass distribution, the mass of FFPs. So we kind of see here that there's quite a few features in here that take right. So you've got this sort of also looking at the different, what stars contribute different planets. We kind of see that circle binaries, or the binaries dominate this area, and then the single star and the planet scatters dominate this area. Okay, so low mass planets ejected from the planet scatter, more massive planets ejected from the circle binary. We kind of see a decreasing slope here, and this is as collisions are becoming increasingly dominant here. Earth mass planets generally hit each other. As you remember, if you saw in a movie, there's a lot of gray points around an Earth mass. Okay. And this leads to a dearth around an Earth mass in the plot. And so this just shows the collision versus ejection distribution. And you kind of see an increase there of 50 collisions per ejection. Okay. Then we have this sort of increased migration around, as you said, around the Mars mass. They start migrating quite quickly, and so everything goes in towards the cavity. This then leads to a lot of ejections in this area, and so this is what causes this pebble isolation mass peak. Additionally, This is also where it kind of transitions from a fast accretion regime. It stops accreting pebbles and starts accreting gas quite slowly. Okay, and this allows a large number of planets to be in this region to then be ejected. And then, as a lot of planets are ejected, we then have a few planets form, and so then we get a lack of giant planets out at the other end. Okay. So just comparing quickly with the observations, and we get this kind of comparing with the assuming slopes effectively, we kind of see a good agreement above about 8 Earth masses. And so we have a slightly different slope line, about 1.2, which is consistent with their results. There's a bit of scattering there. But then we also see this peak and trough, which is not modeled in the observations, obviously, because it's a massive extrapolation down to the low masses. So this would be interesting to see if Roman can see a feature like this. So just quickly to go on to the ongoing work. So I'm improving the model by going to different stellar masses. As I said, this is one set of circular binary simulations, one set of stellar masses, one mass ratio, one binary eccentricity. So going using different stellar masses, varying these orbital parameters here, will give a much better population to actually derive an FFP set of planets from. And it will allow us to actually look at different stellar populations, i.e. star forming regions, different metallicities, thickness, thinness, etc. And so just looking quickly at the how the stellar mass affects everything. So this is each star individually. We find that actually solar type stars, you see this peak here. And so we actually get this super Earths. As you go down in stellar mass, fewer planets are ejected. And most of this is on the formation process. There's fewer planets. Fewer planets obviously form a high mass for low mass stars. But also fewer planets generally form because there's less metals, which fewer metals. Okay. But some of these features still remain. And then obviously this is per star. When we look at the contribution overall, we can actually see that actually the early M dwarfs, which is the red line, actually dominates the contribution to the FFPs. The late M dwarfs, even though there's a lot more of them, they don't form as many planets, so they don't contribute as much. Whereas again, the solar type stars, there's few of those stars, but they form efficiently, so they only actually contribute very few. Okay. But then, so finally, how does this then affect this mass distribution? This is very ongoing, so this is very subject to change as well. This is what I showed previously. Looking at the new model, we kind of actually see that it's moved down a little bit, as I said, and that's because we're now taking account all of these M dwarfs. But we still see there's a nice little peaky or bump feature here. There's also this slope here, but also now it's appearing there's like two power laws effectively. And this is at around about half a Jupiter mass. 0.6 Jupiter mass is where this sort of transition from a very shallow slope to a very steep slope goes in. And this could signify, I'm not sure yet, this is, like I said, very new. This could signify where the end of runaway gas accretion occurs and the planets open gaps, deep gaps in the disk, and they start accreting in a very slow accretion routine. Okay. So I'll leave my conclusions, because I know I'm covering this over. So thank you.
So actually I have 3 questions, and I'll give them all in a row. So first is, what do you assume for distribution of certain binary planets versus planets in certain binary systems versus single star systems? Then also, what about higher mass host stars that have already finished their evolution? Potentially, if they eject many planets, they could distribution. And finally, there's been a couple of papers a while back about really wide binaries that such that their eccentricities are unstable and they can go to they perturb high eccentricity and have close interactions that steal planets or eject planets.
Okay, so I'll do the second one first, which is on the high mass stars. So yes, I haven't got the high mass stars. It could be expected, yes, they will probably form more planets and especially more massive planets. The only caveat would be, just going back to this plot again here, is that there are very few of those stars. So I think they're actually going to be, this is going to continue to go down. So they won't actually contribute many to the overall distribution of FFPs, but they will be performing some. But it's going to be at probably percent level, if that, adding on to what we've already got. It's mainly coming from the low mass stars, because there's more low stars. First point on the comparing circumbinary to single stars, there's only 20 or so circumbinary planets still at the minute, so it's still very difficult to compare that, and it's hard to get down to a think the smallest is about three or four Earth radii. So it's only like 15, 20 Earth masses that can generally get them. So it's very difficult there. From the formation models, migration is an issue on single star formation, but generally I can get similar, I can form similar planets in the planet formation models. It's just getting distributions will be quite different. That still needs a lot of work in the future, but we need to know the certain binary population first. And then on the final point on the wide binaries, the problem there from the formation, this is what I'm going to also do in future work, is yes, you can have the eccentric binaries, but it depends on how eccentric they are. As they come in, they're going to truncate the bits. And that's the big problem. Is not so much on whether they can eject objects, it's how much they affect on whether objects can form. If you're truncating the disk quite often, and down to 20, 30, 40 AU, you don't get a lot of that growth from sort of the Pluto mass up to the Mars Earth mass in pebble accretion, because those pebbles are coming from the outer disk. If you're depleting and destroying the outer disk, you don't get that growth. So that needs a lot more work in the future. Whether they can actually form ejectum wise, they'll do that. But
I mean, I guess for the ultra wide binaries, the suggestion was that eccentricity run stable, so they might not have the high eccentricity until the planets have already formed.
That could be yeah. So in that case, then they will eject what's coming and going up. It needs a lot more.
All right, so I think we have a lot of questions here. So Matthew, I saw you wanted to ask a question. Maybe Ida-san and then maybe Sean quickly. We can fit these all in.
Yeah, really quick. I'm really glad that you're looking at binary populations are really complicated. One question I have about your models is, you fix the separation of the binary, or do you allow? So, okay, have you thought about allowing the companion to evolve and migrate within the cloud and disk of the binary? Because then that could be crazy.
So that I have, well, not properly thought about it, but it's a very complex question to ask, because it depends. There's a lot of ongoing work in Mary from Rich Nelson and George Turpin, but also examples now in unit. And the problem becomes how you then treat the disk, whether it's a viscous disk or an achievement disk. That changes all of the DABT, which is changing separation, changes DEBT. And so which prescription you have changes that a little bit, depends on your disk mass, depends on, it's very complex more, and there's a lot of ongoing work in dynamics to try and understand them.
Yeah, she get it.
Yeah, I have a question about the binary detection. So that if my understanding correct, the planet migrate inward and undergo some gross scattering by the binary system, then they eject.
Yeah, so generally the planets will migrate inwards, they'll interact with each other, and then one of them will push them onto an orbit that then interacts with the other.
Then my question is that in that case, this gas also truncated at some region. Then the planet, even if the planet want to migrate inward, then they stop somewhere. Then so it's not clear for me the gross scattering and that kind of strong scattering occurs when people say planet migration. So
so generally they stop at the cavity edge, which is at the epicenter. Actually, it's at the epicenter of the cavity generally. So it's about 6 AB, 6 times the separation, and then they need pushed into the cavity by another planet, then just go and push them in.
Okay, so by the effect of another one?
Yeah.
Okay.
Yeah. So it becomes very complex.
Yeah.
All right, Sean, finish us off here.
Okay. Sorry, I want to go back to Dave's point about the really wide binary stars. So there's a cool effect in terms of really wide binaries that are more than about a few hundred or 1,000 AU, which is that they're affected, basically their orbits are similar to Oort cloud comets, and that they change in time due to galactic perturbations. And so over billion-year timescales, they end up having, go to really eccentric states, and then they can perturb planetary systems after a long time. And we know this happens because their distribution of eccentricities around really wide binary stars is higher than around mainstream. So I don't know. It's just a good enough.
Yeah, the long term. Yeah, these simulations are around for 20 million years. So there's also the long term evolution of all of this is going to be fun for everything as well. And should add only to these numbers.
All right, so let's thank Gavin again.